So we'll have I minus 1 subtractions. At the very end, we will have m minus 1 subtractions. So the subtractions start with 0 subtractions at step 1, 1 subtraction at step 2, and so on, m minus 1 subtractions at step m. The same with multiplications. At the first step, we don't have any multiplication. The second step, we have this multiplication. At the ith step, we'll have multiplication li1x1 up to lii minus 1xi minus 1. So at step I, we have I minus 1 multiplications. At step m, we have this multiplication and so on up to this multiplication. So from 1 to m minus 1, we end up with m minus 1 multiplications. So the total number of operations is total number of divisions plus total number of subtractions plus total number of multiplications. The divisions are ones every time, m times. So this is the number of the divisions. The subtractions and multiplications, these are twice because they're both for the subtractions and multiplications, and they're the sum of the numbers 1 plus 2 and so on plus m minus 1, which corresponds to that sum. And then, so this m goes to here, and then the sum of the first m minus 1 terms, so 1 plus 2 plus and so on plus m minus 1. There is a formula for the sum of the first m integer numbers. This is the number that you end up with, which here is m minus 1, times the number that you end up with plus 1. So m minus 1 plus 1 will give you m over 2. So that sum here is this. We multiply it by 2. 2 and 2 will cancel out, and this will give you this term. And whenever operation count is concerned, the leading one looks at the leading term. That means the term with the highest power. So the term with the highest power here will be m squared. So the operation count is approximately m squared. Sometimes they write big O of m squared, which means constant times is bounded by a constant times L squared. So let us keep in our mind that if we do forward elimination, which is a method that works only if the matrix is lower triangular matrix, then the operation count is approximately m squared. Similar thing is done when the matrix A is an upper triangular matrix. Since the determinant is different, since A has to be invertible, because these are only the only matrices that we are discussing. The determinant of this matrix has to be different from 0. The determinant of an upper triangular matrix is the product of the elements on the main diagonal. And since the product has to be different from 0, then each term in this product has to be different from 0. And for upper triangular matrices, the method for solving a linear system is called backward substitution. And again, we write AX is equal to B. Instead of A, we write U because A is upper triangular matrix, and then write down what the system is and what the corresponding equations are. And so what we do, we start from the bottom up this time. That's why it's called backward substitution, because we start from the bottom and make all our way up. Why do we start from the bottom? Because if we look at the bottom, there is only one unknown, and this is the xm. If we go to the next to the last equation, then we will have two unknowns, x m minus 1 and xm. So basically the picture is the same as this one, but not from the top to bottom, but from the bottom to the top. And we do the same, we apply the same strategy. Since umm is different from 0, we write xm as the here it is u as a ratio, so it is a misprint, here is u as a ratio of bm and umm, and then we continue to the next equation. By that moment, this will be known, and this will be the only unknown, and therefore the known part will move to the right and divide by this term. and we'll find an expression for xm minus 1. And so on, we make our way up to the last equation. At the very last equation, we will have that all these elements are known, because by the time we reach the first equation, all this will be known. We move them to the right hand side, and we will have the expression for x1. And exactly the same way, we count the operations, and we find out that the operation count is the same, that the operation count is about m squared. Now, we continue with the next method, which is Gauss elimination. Gauss elimination is a very widely used method for solving linear systems. And it is a method that probably you have studied quite intensively in linear algebra. One can view, or at least here in this class, we will view the Gauss elimination method in two ways. We will see how we can use it to solve linear systems AX is equal to B. And also we will use the Gauss elimination as a vehicle to do a factorization of the matrix A, namely as a vehicle to write the matrix A as a product of two matrices, a matrix L, which is a unit lower triangular matrix. So L is a lower triangular matrix, and we add this unit lower triangular matrix because L will be a matrix for which all the diagonal elements are ones. And so A will be a product of a unit lower triangular matrix L and upper triangular matrix U. So when we do Gauss elimination, probably you remember from linear algebra, you end up with an upper triangular matrix, and this U is the upper triangular matrix that you end up with. And then you do backward substitution to actually find the solution of your system. Meanwhile, when you perform the computations in order to arrive at U, you will have some information that you can utilize, and this information can be used to construct the matrix L that participates in this factorization of the matrix A. This factorization of A is called LU factorization of the matrix A. And LU factorization for the matrix A can be achieved not through the Gauss elimination, but it can be achieved through just simply write down the system, write down the unknowns for L, the unknowns for U, which means the entries for L and the entries for U, and then perform in a clever way, perform the necessary the multiplication of those two matrices. And once you do that, you will end up with equations that will determine the entries of L and U. So to the bottom line is that we are going to use the Gauss elimination to write down the LU factorization of the matrix A. That means writing A as a product of a unit lower triangular matrix and upper triangular matrix, or we will see that not every matrix A can be written in this form. If the matrix A cannot be written in this form, we will see that we can find a permutation matrix P such that not A is equal to L times U, but P times A is equal to L times U. So not A by itself is the product of L and U, but if you multiply a permutation matrix times the matrix A, which basically means that we will do some permutation of the rows of the matrix, then we'll end up with a matrix that has the LU factorization. So let's know that what is the goal with the Gauss elimination. The Gauss elimination transforms a full linear system. What do we mean by full linear system? That means that basically all entries are non-zero. So this is a full linear system. All the entries here are not zero. And so what we do is that after, so this is a 4x4 matrix. After performing the Gauss elimination, we end up with the upper triangular matrix. So we have 0 here, and everywhere below the main diagonal we have zeros, and now above the main diagonal we may or may not have zeros, but on the diagonal we are not going to have zeros. So so what is happening is that the Gauss elimination transforms this whole system into an upper triangular system. And how does it do that? It does that by, as you know, you have you stay on a particular row, and then you add to this row another row of the system multiplied by a number. So this is basically a simple linear transformation, and we will see how this can be expressed in terms of matrices. So the idea is to introduce zeros below the diagonal in the columns of the matrix. So here we see the goal is to find to make everything below the main diagonal 0. And what is the execution? So if one thinks about the execution, we subtract multiples of each row from subsequent rows, if you remember from linear algebra. And this action, subtracting multiples of each row from subsequent rows, actually can be achieved by multiplying the matrix A on the left by a particular a sequence of lower triangular matrices LK. So we have the matrix A, and then let's say we have AX is equal to B. Or we can we may not associate the matrix to the system. We may think of doing an LU factorization of the matrix A without associating it to a particular system. Now, if what we want, so we start with our original matrix. Here, our original matrix has some entries, which are stars and have index 1. That means these are all the entries at the first step. Then what we do is we multiply to the left the matrix A with the matrix L1, which is a lower triangular matrix, and we will see how to find it. The matrix A by the matrix L1. And as a result, the resulting matrix, which we denote by A2. So A2 is L1 times A1. This will be the resulting matrix. After this multiplication, so A2 is equal to L1 times A. And this matrix will have zeros everywhere below the main diagonal on the first column. This row will stay the same as the original row. So the elements of this row will be the same as the elements of this row here. But these elements here now will be different because some algebraic operations are performed on those. And these elements will be different from the corresponding elements and these positions in the matrix A. Now we multiply this matrix by lower triangular matrix L2. And as a result, we will end up with the matrix. So this will be L2 times L1 times A. And as a result, so we will keep unchanged the first row. We will keep here unchanged the second row. We will have that below the second column, everything is 0. So this will be 0, which we basically will make this element 0. And then these elements here, they will change because we'll do some arithmetic operation over them. So they will be the elements that will be the elements of this matrix. And then the last step will be we multiply this matrix on the left by a lower triangular matrix L3. When we do that, we will end up with this matrix, which will be L3 times L2 times L1 times A. And at the same time, this will be the upper triangular matrix that we are looking at, because after this multiplication, we will have the first row unchanged. We will have from the previous step, we will have the second row is unchanged from the previous step. We will have this row here unchanged from the previous step. Everything below the diagonal on the third column will be equal to 0. So this will be 0. And then the only thing that will be changed then will be this term here from the previous step. So we will have that. So now let's come back. This is in the case of 4 by 4 matrix, and in general, in the case for M by M matrix, what we will end up is that we will end up multiplying the matrix A on the left by a sequence of lower triangular matrices. And as a result, we will end up with the matrix U. So now if we look at the multiplication of those matrices, this will be also a matrix of dimension M times M. And we will see that this matrix will be invertible. And if we write this matrix as L inverse, so what we will have L inverse times A is equal to U. And if we multiply both sides on the left by L, we will have that the matrix A is equal to L times the matrix U. And this is the LU factorization that we were discussing. Now, if L inverse is equal to those matrices, because we denoted by L inverse the product Lm minus 1, then we have Lm minus 2, and so on, we have L2 and L1. To find what is L, L then will be the inverse of all those matrices. So will be Lm minus 1 up to L2 times L1, and this is the inverse of all these matrices. And then using the rule for finding an inverse of a product, this will be exactly L1 inverse times L2 inverse, and so on times Lm minus 1 inverse. So what we need to do is we need to first find how the multiples, how this operation, subtracting multiples of each row from subsequent rows, can be done by multiplying the matrix A on the left by particular lower triangular matrix. So we have to determine what all those matrices are. And we have to see that they are such that when we look at their inverses and when we multiply them, we end up with a matrix that is a lower triangular matrix. And then we will have that the matrix A can be represented as a product of a lower triangular matrix that have ones on the main diagonal and an upper triangular matrix. So basically this is in a nutshell the idea of Gauss elimination, how to construct the matrices L. The matrices, the final matrix L is actually never, if we want to solve the system, is never constructed. But if we want to, never constructed explicitly, but if we want to look for the LU factorization for the matrix A, then we can and should save it every time we do the computation. So now, if we go further with the Gauss elimination and look at the details, what we have here is that let's stick to the notation that the matrix that we begin with, we associate with index, upper index 1. Here is lower, but here is upper index 1 of its entries. Then the matrix after the first step, we associate with an upper index 2. So we see here that after the first step of the Gauss elimination, the first row is not changed. So here, these entries will be the same as the first row of the original matrix, and then the entries that will change will be the entries of this submatrix. They will be different from the entries of this submatrix of the original A. And then all the elements below the main diagonal on the first row will be equal to 0. And in general, at the kth step, what we are going to have, the matrix AK will have the following structure. The elements will have some elements on the main diagonal up to here. Then this will be the element AKK. So this will be this element here, which is called the pivot element AKK. And then we'll have some elements below the main diagonal. So here, this is a kth row. And here, this is the kth column. So the elements on the kth row and the kth column at the kth step. Here, everything will be 0. As you can see, all the elements here will be 0. And then what we are going to change, we are going to change, so this is the element AKK, we're going to change all the elements that are below, right here, below the kth row. So all these elements here, the next step will be changed. And all these elements that are in blue at the next step will end up with 0. So how do we do that? If we look at the first step, and as I said, the element AKK is called the pivot element. So if we look at the first step, what we do at the first step, we multiply, we want to make all these terms here 0. So we want to make this term 0, and so on. We want to make this term 0. What do? We assume that A111 is different from 0, and therefore we can multiply. In order to make this term 0, we have to multiply the first row by a number such that when we add it to this row, we will make this term 0. And what do we multiply it by? We multiply it by A211 divided by A111 with a negative sign. So if we multiply the first row by that number and add it to the second row, A11 with A111 will cancel out. Then we will have minus A21, which added to A211 will make it 0, and then we will end up with 0 here. And then this will change all the subsequent elements in this row to these elements with an index 2. This way we make the term A211 to be 0. Then what we do, we look at the first row, and we want to move to make the element on row 3, the first element on row 3, so it will be A311, and then we'll multiply it not by this number, but we'll multiply it by the number minus A131 divided by A11. Then if we multiply the first row by that number and we add it to the third row, then we will make the corresponding term in the third row 0, and we will change also the subsequent elements in this third row. This is what is happening after the first step. And in general, if we look at the kth step, then what is happening in at the kth step? In order to continue with these steps, we see that for the first step, the element A11 has to be different from 0. Then we arrive from the matrix A1 to the matrix A2. Now we basically repeat this operation. We forget about this part of the matrix, and then we concentrate only on this matrix. If we do operations between the rows from the second to the nth, these operations will not affect the first terms of this row because they're all 0. And now we can do exactly the same. What we did for the first matrix, we can do it for this submatrix. In order to do that, the element A22, which is the second pivot element, has to be different from 0, and so on. Here, if we come to the kth step, at this step, we now forget that we had done all the job for the first k-1 rows, so we don't need to touch them anymore. That's why if you see here, they will be kept whatever they were up to that stage, and the only change will happen at row k plus 1, and so on up to row m. So all the change will happen in this submatrix. And then what we want to do, we want to make all these blue numbers here zeros. And how do we do that? We multiply the first row by the number a k plus 1 kk divided by a k with a sign minus. If we do that, then AKK will cancel with LKK, and then as a result, in the first term of this row here, we'll have minus AK plus 1K, which will added to this term will make it 0, and we will also have modified the rest of the elements in this row. If we write down the actual formulas, then the formulas are the following. First, we compute the numbers LJK, which are exactly, if you see, these are those numbers, AK plus 1 KK divided by AKK. So those numbers are all, the numbers LJK will be all the numbers that have in the denominator AKK, and in the numerator they will have AJK when J is from K plus 1 to M. So how do we remember those? So how do we get, for example, the number LK plus 1K? This number is this term divided by the corresponding pivot. So this will be AK plus 1KK divided by the pivot AKKK. Then what will be the next one? K plus 2K. Then it will be the element that stays on the K plus second row and kth column. So it will be AK plus 2KK divided again by the corresponding pivot element AKKK. And this is exactly what is written here. It's just that the index J here, it is written in terms of the index J, and J runs from K plus 1 to M because it starts from this K plus 1 here and runs up to M. So we make these numbers, and these are exactly the numbers that we will multiply the kth row. You see here, this is the number, this is exactly the number L K plus 1K. And this is the number that we will multiply the kth row. So what we do is to make the change, and we know that when we do this operation, then all the elements in this column here will be equal to, this part of the column will be equal to 0, and then we're gonna make change only here, and then the new elements, that the new entries of the matrix, we denote them by index K plus 1 because they will be changed. And what will they be? They will be the old entries that stay there, which are denoted by index K, so all the AJKs that stay there, and then minus, because we want the sign minus in order to make 0 these blue terms, minus the element LJK, which we know how to compute, and we know we want it because we want to make the blue element 0, times the corresponding element AK IK. So times the corresponding element that is on the ith row, where the row is here, and on the kth column. So this is this corresponding element of this pivot, I would say pivot row that stays on the ith column, because this is the element AKIK. So we have minus LK the corresponding L term multiplied by that element and add it to the corresponding term that stays in this position, Jik. So this is the main algorithm or the main rules by which we perform Gauss elimination at step k, for k from 1 to m minus 1. And they all involve here making the idea is to make all the blue terms at step k to be 0. This is the Gauss elimination. And this is can be done only if every time after every step, the pivot element that shows up, which is the element here in the corner of the submatrix, the pivot element that shows up is a non-zero element. Only then we can do that, because only then we can compute the numbers L, J, K. And now the claim is that if you look carefully at what these equations give you, and then if you look carefully at the matrix LK, which I will explain how to construct, then you will see that these operations here written on these two rows actually can be done by multiplying the matrix AK on the left by the matrix LK. So how do we construct the matrix LK? If we look back here, we know that at step K, we are at row K and column K. So this is the column K. Now, what we do is we construct the matrix LK the following way. We write identity matrix everywhere. And then we look at the column K. So this is column K. The column K will hit here the identity where this is the row K. And then what we have here is row K plus 1 after the row K, and so on. We'll have here row M. What do we put on row LK plus 1? We put the element LK plus 1K. Then on row K plus 2 and column K, we put LK plus 2K and so on. And this is exactly what is written here with a negative sign. So we have the identity matrix. This is the identity matrix. This is the kth column. And this is part of the kth column that lives below the main diagonal. We populate only this kth column with the negatives of the numbers L, which are what numbers? Which are, we look at this number AK plus 1K at step K divided by the pivot and write down the index, which is the same as the existing index K plus 1K. And so on up to the last term here. We look at this term, we divide it by the pivot element and populate the matrix at this, give it index MK and write it down as an index right here with a negative sign. So if you write down the matrix LK and you look at the LK times the matrix AK, so what will happen is if I have here the matrix AK, we know that the matrix AK has the following structure. So here is this pivot element AKKK, and here is something is happening. Here is the main diagonal, and here everything is 0. And using the rules for multiplying two matrices, once you write down carefully what this multiplication is, you will find out that this operation here is the same as multiplying the matrix AK on the left by the matrices LK. So this will be the end of the lecture. What we will do next time, we will discuss properties of this matrices LK. And we also will discuss how the Gauss elimination is performed for matrices that are have some matrices that have special structure. Okay, Thank you. See you next time.